In January of 2026, a team of astronomers at MIT confirmed something that should not exist: a galaxy fully formed, blazing with hundreds of millions of stars, existing just 280 million years after the Big Bang, when the universe was barely 2% of its current age. The lead scientist looked at the data and said, "We can see farther than humans ever have, and it looks nothing like what we predicted." That one sentence is the reason this documentary exists. Because if the universe looks nothing like what we predicted, and to understand why that discovery is so unsettling, we need to start somewhere much closer to home, with the thing you look at every single night and completely misread. There is something quietly deceptive about a clear night sky, and it has nothing to do with clouds or light pollution. It has to do with the fundamental nature of what you are actually seeing when you look up. Every single star visible to the naked eye, every one of them, sits within a region that covers less than 1% of the Milky Way's total diameter. The galaxy you live in stretches roughly 100,000 light years across, which means light traveling at 300,000 kilometers per second, fast enough to circle the entire Earth 7 times in a single second, still needs 100,000 years to cross it from one end to the other. And the stars you can see with your bare eyes are all crammed into a tiny neighborhood near our position, which itself is tucked into a quiet outer arm of the galaxy, nowhere near the center, nowhere near anything particularly notable. So when you look up at night and see what feels like the whole universe sprawled above you, you are actually looking at the cosmic equivalent of standing in your living room and thinking you have seen the whole city. But here is the part that goes a level deeper, and it is something most people never fully sit with. The night sky is not a photograph of the universe as it currently exists. It is not even a photograph at all. It is a collage, a layered, temporally scrambled collage, where every single point of light belongs to a completely different moment in time. The star that sits just a few degrees to the left of the one you are looking at might be 400 light years away, which means the light reaching your eye left that star 400 years ago, around the time Galileo was first pointing a telescope at the sky. The star right next to it might be 12,000 light years away, meaning that light has been traveling since before the last ice age ended, before the first human civilization built anything, before we had a written word for any of it. Both stars appear side by side on the same flat canvas of your vision, but they belong to entirely different chapters of history, separated by thousands of years, stacked on top of each other with no label, no timestamp, no indication that what you are seeing is not a single moment, but dozens of moments compressed into one. The farthest object a human being can see without any equipment is the Andromeda Galaxy, which sits about 2.5 million light years away and appears as a faint smudge just above the constellation Cassiopeia on a dark enough night. The light you are receiving from Andromeda right now left that galaxy 2.5 million years ago, before the species Homo sapiens existed, before our direct ancestors had stone tools of any sophistication, at a time when the creature that would eventually become you was something else entirely, walking a different continent, living under a sky. It could not conceptualize that light has been crossing empty space for all of that time, and it arrives at your eye in this specific moment, this specific night, indistinguishable from every other smudge of light around it. The night sky, in other words, is not a view of the universe. It is a museum of time, and every exhibit is from a different era, displayed without any chronological order, presented as though they are all happening simultaneously when they are not, and never were. And Andromeda, that 2.5 million year old signal reaching your eye, is still our nearest large galactic neighbor. It is still on the scale of the observable universe, essentially next door, which means that the deception goes so much further than just the stars you can see. The Milky Way itself contains somewhere between 200 and 400 billion individual stars, a number so large that if you tried to count them one per second, without stopping, without sleeping, it would take you roughly 10,000 years just to finish. And yet, the Milky Way is just one of roughly 2 trillion galaxies within the observable universe, each containing billions of stars of their own, each sitting at distances so vast that the light from the closest ones took millions of years to arrive, and the light from the farthest ones has been traveling for over 13 billion years, launched before our solar system existed, before the Earth had cooled, before any of the atoms that make up your body had been assembled by a dying star. All of that is out there. None of it is visible to the naked eye. The entire theater of human stargazing. Every myth, every constellation, every navigator who ever used the stars to cross an ocean was based on a sample size of less than 1% of one galaxy out of 2 trillion. That is how thoroughly the night sky has been lying to you. And if the visible sky is already that misleading, if what looks like the whole universe is actually just a thin slice of one neighborhood inside one galaxy, then the question worth asking is, how far does the actual scale go? And the answer starts not with distant galaxies, but with a single spacecraft, launched in 1977, that has been flying in a straight line ever since, and has barely gone anywhere at all. On September 5th, 1977, NASA launched a spacecraft called Voyager 1 from Cape Canaveral, Florida. It has been flying continuously ever since, through the outer solar system, past Jupiter, past Saturn, past the orbit of every planet humanity has ever named, and as of right now, it is the farthest human-made object in existence, sitting at a distance of about 25 billion kilometers from the Sun. 25 billion kilometers. That number sounds staggering until you start doing the comparison, at which point it becomes something else entirely. A radio signal, traveling at the speed of light, the same 300,000 kilometers per second that circles the Earth 7 times per second, currently takes more than 23 hours to travel from Voyager 1 back to the receivers on Earth. Engineers at NASA send a command, and they wait nearly a full day to find out if Voyager received it. By the end of 2026, that delay will cross 24 hours. Voyager will become the first human-made object so far away that a round-trip communication takes 2 full days, not because of any technical limitation, but simply because of how much empty space sits between that spacecraft and the planet that built it. And yet, for all of that distance, for all of those billions of kilometers and decades of continuous travel, Voyager 1 has not left the solar system, not even close. The solar system, properly defined, does not end at the last planet. It ends at the outer boundary of something called the Oort cloud, a vast, roughly spherical shell of icy objects that surrounds the Sun at enormous distance, marking the edge of the Sun's gravitational influence, the outermost limit of the territory that belongs, in any meaningful sense, to our star. The inner edge of the Oort cloud begins somewhere around 2,000 times the distance from the Earth to the Sun. The outer edge extends to perhaps 100,000 times that distance, so far out that it sits roughly 1 to 2 light years away, meaning light itself needs 1 to 2 years to cross from the Sun to the outer Oort cloud boundary. Voyager 1, traveling at approximately 61,000 kilometers per hour, faster than any bullet ever fired, faster than anything a human being has physically built and launched, will reach the inner edge of the Oort cloud in approximately 300 years. It will then spend another 30,000 years crossing through it before finally, technically, leaving the solar system altogether. 30,000 years to exit one star's gravitational neighborhood. To put that in human terms, 30,000 years ago, Homo sapiens had not yet painted the cave walls at Lascaux. The last woolly mammoths were still alive. Agriculture had not been invented. Writing did not exist. Every civilization that has ever risen and fallen on this planet, Mesopotamia, Egypt, Rome, every empire and dynasty and nation that history books record, all of that happened within a span of time that is less than 1/6 of how long it will take Voyager 1 just to clear the outer edge of our own solar system. And after that, after 30,000 years and the Oort cloud boundary and technically leaving the solar system, Voyager 1 will still be nowhere near the next star, Proxima Centauri. The closest star to our own sun sits 4.2 light years away. At Voyager's current speed, reaching it, if Voyager were even pointed in that direction, which it is not, would take approximately 4,000 years. 4,000 years to reach the nearest star, not the nearest interesting star, not a star with confirmed planets, just the nearest one, the one right next door. Cosmically speaking, now here is the thing about Voyager that most people know but very few have really absorbed. It carries a message. Bolted to the side of both Voyager spacecraft is a 12-inch gold, plated copper disc called the Golden Record, containing sounds and images from Earth, music from dozens of cultures, greetings in 55 languages, the sound of wind and rain, a mother's first words to a newborn child, a diagram showing where Earth is located in the galaxy, instructions for how to play the record, and encoded within it all, a kind of portrait of what humanity is and where it comes from. It was sent as a message to whoever might find it. But here is the physics of that gesture. At Voyager's speed, that record will not pass within 2 light years of any star for at least 40,000 years. The universe is so vast, the distances between stars so incomprehensibly large, that the most ambitious thing humanity has ever physically launched into space, carrying our music, our languages, our attempt at contact, will drift through empty interstellar space for longer than our entire civilization has existed before it gets anywhere near anything. That is not a failure of engineering. That is the architecture of the universe, telling us something about itself. And the question that Voyager quietly raises, whether anything else is out there, and whether we could ever actually reach it, does not get easier when you zoom out further. Because when you pull back from the scale of one solar system and start looking at the space between galaxies, the universe does something that nobody expected. It becomes mostly nothing. Here is something that the standard map of the universe does not make obvious. Most of space is empty, not just empty in the way that the space between planets is empty, or the space between stars, but empty in a far more absolute sense. Vast regions, hundreds of millions of light years across, where there are almost no galaxies at all, where the matter that makes up stars and planets and everything we have ever interacted with simply does not accumulate, where the cosmic web of structure just stops. These regions are called voids, and they are not the exception. They are the dominant feature of the large-scale universe. When astronomers map the distribution of galaxies across cosmic scales, what they find is that galaxies are not spread evenly through space. They are concentrated along thin filaments and sheets, like soap film stretched between bubbles. And the bubbles themselves are the voids. enormous, roughly spherical regions of near emptiness that make up the vast majority of the universe's total volume. The most studied of these is called the Boötes void, discovered in 1981, when a team of astronomers conducting a galaxy survey found an enormous gap in the distribution of galaxies in the direction of the constellation Boötes. A gap so large, so thoroughly empty, that it initially seemed like an observational error. It was not. The Boötes void stretches approximately 330 million light years across, and within that entire volume, only about 60 galaxies have been found, where standard models would predict something closer to 2,000. 60 galaxies in a space 330 million light years wide. To understand what that means in human terms, consider this. If the Milky Way were located at the center of the Boötes void rather than where it actually is, astronomers on Earth would not have discovered that other galaxies exist until the 1960s. Not because the technology was not advanced enough, but because the nearest neighboring galaxy would have been so far away, so thoroughly beyond the reach of any earlier telescope, that for the entirety of recorded human history, the universe would have appeared to consist of exactly one galaxy, ours. Every ancient astronomer, every medieval scholar looking at the sky, every early modern scientist who ever pointed an instrument at the heavens, would have seen a universe that appeared to be simply the Milky Way and nothing beyond it. Not because that was wrong, but because the actual neighbors were too far away to see. That is how large a void can be. But the Boötes void is not where we live. Where we actually live is inside a somewhat different structure. Less extreme, but arguably more significant because it is ours. It is called the KBC void, named after the astronomers who characterized it. And it is a large local underdensity, a region roughly 1 billion light years across, where the density of matter is approximately 20% lower than the cosmic average. Not as dramatically empty as Boötes, but measurably, consistently less dense than the universe overall, confirmed across observations in multiple wavelengths of light, in galaxy counts, in the velocity fields of surrounding matter. The Milky Way sits in this void. The entire local group of galaxies, the Milky Way, Andromeda, and their roughly 50 smaller companions, sits in this void. And the implications of that, as it turns out, reach much further than just the question of whether we live in a sparse neighborhood, because a void is not static. Matter does not stay evenly distributed when there is an underdense region in the universe. It flows. Gravity pulls matter from low density regions toward high density regions, which means the matter around the KBC void is being pulled outward toward the denser walls and filaments surrounding it. And that outward flow generates a kind of artificial boost to the local expansion rate, a systematic inflation of how fast nearby galaxies appear to be receding. And that boost, that locally elevated expansion rate, is one of the leading candidates for explaining a discrepancy in our measurements of the universe that has been building in severity for years, and which we will come back to in detail. For now, what matters is the structural fact. We live inside a cosmic hole, one that is measurably less dense than the universe around it. And we have been making measurements of the entire cosmos from inside that hole without always accounting for what that means. But voids alone are only half the picture. The other half, the part that shows what all that displaced matter actually does, requires pulling back further to the level where the full architecture of the universe becomes visible for the first time. When astronomers map the universe at the largest scales, plotting the positions of millions of galaxies across hundreds of millions of light years, what appears is not randomness. It is not a uniform fog of evenly scattered galaxies. What appears is a structure so intricate, so geometrically precise, and so strangely familiar that it has generated more genuine philosophical double takes among scientists than perhaps any other observation in modern cosmology. The universe, at the largest scales, looks like a web. Specifically, it looks like a vast three-dimensional network of thin filaments, thread, like strands of gas and dark matter, hundreds of millions of light years long, that intersect at dense nodes where galaxy clusters accumulate, with enormous empty voids occupying the space between the filaments, exactly like the spaces inside a sponge or the gaps between the threads of a net. Astronomers call this the cosmic web, and it is not a metaphor or a rough approximation. It is the actual observed structure of matter in the universe. At the largest scales we have mapped, the filaments themselves are composed primarily of dark matter, which we will discuss in more detail shortly. With ordinary matter, the gas that eventually forms galaxies and stars, concentrated along the dense regions where filaments intersect, galaxies are not floating freely through space. They are embedded in this web, gathered at its nodes, strung along its threads, their positions determined by a scaffold that we cannot see directly, but can infer from the distribution of everything we can see. The largest single structure identified within this web is called the Hercules, Corona Borealis Great Wall, a massive concentration of galaxy clusters and filaments that stretches approximately 10 billion light years in its longest dimension, meaning that light, traveling at its maximum possible speed, would take 10 billion years to cross it from one end to the other. And the universe itself is only 13.8 billion years old. This structure is so large that it challenges the standard cosmological assumption that the universe should be roughly uniform at the very largest scales, an assumption that is increasingly looking like it may need revision. Now, here is the thing that has generated genuine scientific bewilderment. When you look at a high-resolution image of the cosmic web alongside a high-resolution image of a slice through the human brain, the network of neurons, the synaptic connections, the clustering at nodes and branching along threads, the structural similarity is remarkable enough that multiple peer-reviewed papers have been written specifically about it. The mathematical properties of the two networks, the clustering coefficient, the degree distribution, the way information or matter concentrates at high connectivity nodes are, in several quantifiable respects, similar. This does not mean the universe is conscious. It does not mean there is any physical connection between neural networks and cosmic structure. What it means is that the same underlying mathematics, the same principles of how things cluster under certain conditions, appears to produce similar geometries at scales, separated by a factor of roughly a trillion. Whether that is a profound coincidence or a hint at something deeper about the nature of structure itself, nobody has resolved. It is simply there, sitting in the data, waiting. And what the cosmic web is built from, what gives it its shape, what provides the gravitational scaffolding that holds the filaments together and determines where galaxies form and where they do not, takes us to one of the most uncomfortable facts in all of modern science. Everything described so far, every star, every galaxy, every filament in the cosmic web, every void, every planet, every atom that has ever been observed or measured or touched, accounts for approximately 5% of the total energy content of the universe. The other 95% is divided between two things that we know exist because the math requires them to, but whose fundamental nature, what they actually are, what they are made of, how they work at a physical level, remains, after decades of increasingly sophisticated experiments, completely unknown. The first of these is called dark matter, which constitutes roughly 27% of the universe's total energy content. The word dark here does not primarily mean that it is visually dark. Though it means that it does not interact with light in any way that has ever been detected. It does not emit light, does not absorb light, does not reflect light. Every instrument that detects light in any part of the electromagnetic spectrum, visible, infrared, X-ray, radio, is completely blind to dark matter. The only reason we know it exists is that its gravitational effects are clearly and consistently measurable. Galaxies rotate at speeds that the visible matter alone cannot explain. Galaxy clusters bend light to a degree that requires far more mass than the stars and gas account for. And the large-scale structure of the cosmic web, the filaments, the voids, the web-like distribution of galaxies, could not have formed the way it did without a vast scaffold of invisible mass providing the gravitational framework. The most dramatic direct evidence for dark matter comes from an event called the Bullet Cluster, two massive galaxy clusters that collided and passed through each other billions of years ago. When astronomers mapped the distribution of ordinary matter after the collision using X-ray observations and compared it to where the gravitational mass was concentrated using a technique called gravitational lensing, they found they were in completely different places. The ordinary matter, the gas, had been slowed by the collision, piling up in the middle, but the gravitational mass had passed straight through, undisturbed, continuing in its original direction as though the collision had not happened at all. Two separate components of each cluster, separated by the violence of an intergalactic collision, moving independently, confirming that the mass and the visible matter are not the same thing and do not behave the same way. Dark matter is real, it is just that nobody knows what it is. The second unknown is dark energy, which accounts for the remaining 68%. And it is in some ways even stranger than dark matter. Dark energy is not a substance in the ordinary sense. It is a property of space itself, a kind of pressure or tension built into the fabric of the universe that causes the expansion of space to accelerate rather than slow down over time. Every galaxy that is not gravitationally bound to the Milky Way's local neighborhood is being carried away from us by this expansion, and the rate at which it is being carried away is not constant. It is increasing. The universe is not just expanding, it is expanding faster and faster, driven by an energy that fills all of space uniformly, that has no source in any object or particle, and that increases in total quantity as the universe grows larger. This last property, the fact that dark energy increases as space expands, is what makes it truly unlike anything else in physics. Ordinary matter and energy become more dilute as the universe expands, their density decreasing as the volume increases. Dark energy does not. It maintains constant density as space grows, which means that as the universe gets larger, the total amount of dark energy increases, and the acceleration it produces intensifies over time. Combined, dark matter and dark energy account for 95% of everything the universe contains, and we have no direct detection of either one. The entirety of human knowledge, every scientific instrument ever built, every observation ever made, every theory ever tested, applies to the 5% remainder. We are, in the most literal possible sense, studying a thin surface layer of something whose interior we cannot access, drawing conclusions about the whole from a sample that represents 1 in 20 parts of the total. And within that 5%, there is still a force pulling us in a direction we cannot see. The Milky Way is moving, not just rotating. All galaxies rotate. but moving through space, carried by gravity towards something large enough and massive enough to pull not just our galaxy, but hundreds of thousands of neighboring galaxies in the same direction. At a speed of approximately 600 kilometers per second, that is 600 kilometers, roughly the distance from London to Edinburgh, covered every single second, by the entire Milky Way galaxy, by every star in it, including our Sun, by every planet orbiting those stars, including Earth, including you, right now, continuously. The gravitational source responsible for this motion is called the Great Attractor, and it sits approximately 250 million light years away from us in the direction of the constellation Centaurus. It is not a single object. It is a region, a convergence point in the large-scale structure of the universe, where matter has accumulated to a concentration massive enough to exert gravitational influence across hundreds of millions of light years. Its estimated mass is roughly 100 trillion times the mass of the Milky Way, which is already itself a structure containing hundreds of billions of stars. The problem is that we cannot observe it directly. The Great Attractor sits almost perfectly behind the galactic plane, the densely packed disk of stars, gas, and dust that forms the visible band of the Milky Way across the sky, in a region that astronomers call the zone of avoidance, where our own galaxy blocks and obscures the view in visible light. For decades after the Great Attractor was first identified in the 1980s through its gravitational effects on galaxy motions, nobody could see what was actually there. X-ray surveys and infrared observations have since peered through the obscuration, but the picture remains incomplete. And what has emerged from those observations is, in some ways, more disorienting than the original mystery. Because the Great Attractor itself is not the final destination. The Great Attractor is the gravitational focal point of a much larger structure called the Laniakea supercluster, a vast basin of gravitational attraction containing approximately 100,000 galaxies, stretching roughly 520 million light years across, with a total mass equivalent to roughly 100 million billion times the mass of our Sun. The Milky Way is one galaxy among 100,000, sitting somewhere in the outer regions of this supercluster, being pulled, along with all its neighbors, toward the center. But Laniakea itself is moving. The entire supercluster, all 100,000 galaxies, all that mass, the Great Attractor, and everything being pulled toward it, is being drawn in turn toward an even larger concentration of matter called the Shapley supercluster, which sits approximately 650 million light years away and exerts gravitational influence across a sphere of space roughly 1 billion light years in radius. And Shapley itself may be part of something larger still, a chain of gravitational influence that extends further than current maps can follow. Here is the consequence of all of this that is worth sitting with. We do not know where we are going, not in a philosophical sense, in a literal, astronomical sense. The Milky Way is moving at 600 kilometers per second toward a destination that is obscured by our own galaxy's disk, which is itself being drawn toward a supercluster center, which is being pulled toward a larger concentration behind it, in a chain of gravitational pulls that current observations cannot fully trace. The direction of our motion through the cosmos is partially hidden from us by the very structure we are part of. There is also a catch about the destination. Even setting aside the question of what it is, we will never arrive. Laniakea is not gravitationally bound. Dark energy is expanding space fast enough that the outer regions of the supercluster are being pushed apart, even as gravity tries to pull them together. And the net result is that Laniakea, as a coherent structure, will eventually disperse, torn apart by the accelerating expansion before it ever collapses, We are moving toward a center that will dissolve before we reach it, pulled by a force working against an expansion that will ultimately win. But before that expansion wins, before any of that plays out across billions of years, there is a more immediate question about where exactly we stand in all of this, and what address we would give if someone in another galaxy asked us where to find us. There is a kind of clarity that comes from stating your position in full, without abbreviation, at every scale from the smallest to the largest. And for a human being on Earth in the 21st century, that address goes something like this. You are on a planet orbiting an average-sized star in the outer edge of a spiral arm called the Orion Arm, which is one of the minor arms of a barred spiral galaxy called the Milky Way, which contains between 200 and 400 billion stars and stretches 100,000 light years across. The Milky Way sits within a small group of roughly 50 galaxies called the Local Group, which is dominated by the Milky Way and the Andromeda Galaxy, but is, by the standards of galaxy clusters, a modest and relatively quiet neighborhood. The Local Group is itself embedded within the Virgo supercluster, which is in turn part of Laniakea, the 520 million light the year basin of gravitational attraction described above. Laniakea sits within the KBC void, the large local underdensity that is approximately 20% less matter, rich than the cosmic average. And all of this sits within the observable universe, a sphere roughly 93 billion light years in diameter, containing approximately 2 trillion galaxies, which is itself only the portion of the total universe that light has had time to reach us from since the Big Bang. Each level of that address is larger than the previous one by a factor that is, in human terms, incomprehensible. The distance from Earth to the Moon is roughly 30 times the diameter of the Earth. The distance from the Earth to the Sun is about 400 times the distance to the Moon. The distance from the Sun to the next star is about 270,000 times the distance from the Earth to the Sun. The diameter of the Milky Way is about 6 billion times the distance from the Earth to the Sun. The diameter of the observable universe is about 900,000 times the diameter of the Milky Way. Each step is not a linear increase. It is a multiplication, compounding on itself. Each scale so much larger than the previous one that the numbers stop carrying meaning and can only be gestured at through comparison. And within all of that, at every level of the address, the Milky Way's position is unremarkable. We are not at the center of the galaxy. We are in the outer suburbs. We are not in the densest part of the Local Group. We are one of the 2 largest members in a small cluster. We are not in a particularly notable part of Laniakea. We are in the outer reaches of a supercluster that is not gravitationally bound and will not survive. We are in a void, a region with below average matter density, rather than in one of the rich filaments where galaxy clusters concentrate. And the observable universe itself is, as we will see, almost certainly not the full extent of what exists, but only the portion whose light has reached us so far. None of this is presented as a reason for despair. It is simply the map, and having the map matters, because the map is what makes the questions possible. And the questions are what make the next part of this story so genuinely strange, because there is a wall around everything described so far. A boundary that is not physical, not a wall in the sense of something you could hit, but a limit that is absolute and imposed by the structure of reality itself, and what sits just inside that wall. What the oldest light in the universe has been telling us, and what sits on the other side of it, are 2 of the most disorienting things in all of modern science. The observable universe has a boundary, not a wall in any material sense, not an edge where space ends, but a horizon, a distance beyond which no information has ever reached us. Not because the universe does not continue beyond it, but because light from those regions has not had enough time, in the 13.8 billion years since the Big Bang, to travel to where we are. This is a subtle but important distinction. The boundary of the observable universe is not a boundary of the universe itself. It is a boundary of our visibility, determined by the finite speed of light and the finite age of the cosmos. Beyond that horizon, space continues. Most cosmologists believe it continues for an enormous distance, possibly forever, but we cannot see any of it, cannot receive any signal from it, cannot know anything about it through direct observation, because the light from those regions is still in transit. Now, here is the thing about that boundary that initially seems like a mathematical error but is actually correct. The observable universe has a radius of approximately 6.5 billion light years, even though the universe is only 13.8 billion years old. How can we see 6 billion light years in a universe where light has only had 13.8 billion years to travel? The answer is expansion. Space itself has been expanding throughout the entire history of the universe, which means the matter that emitted the light we are receiving today was much closer to us when it emitted that light, and has been carried away by expansion ever since. The light left from a relatively short distance, crossed an expanding space, and the source of that light is now much further away than it was when the light departed. The 46 billion light. The year figure is the current distance to those sources, accounting for how far they have been carried by expansion during the time the light was traveling. The oldest light we can receive, the absolute oldest signal that any instrument on Earth or in orbit can detect, is called the cosmic microwave background, and it comes from approximately 380,000 years after the Big Bang, which is the moment when the universe cooled enough for the first stable atoms to form. Before that moment, the universe was so hot and dense that light could not travel in straight lines. Photons were constantly scattering off free electrons, making the early universe completely opaque, the way that fog scatters light so thoroughly that you cannot see through it. When atoms formed, the electrons were captured and the fog lifted, and all the light that had been trapped in that scattering was suddenly free to travel. That light is what we detect today as the cosmic microwave background. Faint, microwave radiation arriving uniformly from every direction in the sky, carrying a snapshot of what the universe looked like at 380,000 years old. It is the first photograph the universe ever took of itself, and it is the furthest back any telescope can see. Before the CMB is a wall, not of matter, but of opacity, beyond which no electromagnetic signal of any kind can reach us, because the universe was simply too thick with scattering particles for light to have escaped. But here is what makes the boundary genuinely troubling rather than merely limiting. It is shrinking, not the boundary itself, but the number of galaxies within it, because dark energy is accelerating the expansion of space. Galaxies that are currently just beyond a certain distance are already receding from us faster than light can travel, which means any light they emit right now will never reach us. Not because it is too far away today, but because space is expanding fast enough between us and those galaxies that the light can never gain ground. They have crossed what physicists call the event horizon, and they are gone from our universe in any observational sense. Current estimates suggest that roughly 97% of the galaxies in the observable universe have already crossed the event horizon, meaning the light we see from them is the last light we will ever receive. And it was emitted in the past, not today. The 3% that remain reachable are being pushed across the horizon continuously. In roughly 150 billion years, If any observers remain, they will look out at a nearly empty sky, with no evidence that the billions of galaxies we can see today ever existed, because all of that light will have been stretched beyond detectability. All of those galaxies pushed irreversibly beyond reach. The universe is not just large, it is becoming less knowable over time, its own structure working against the ability of any observer to understand the whole. And it was in this context, with this understood, with the boundary of the observable universe mapped, and the fate of that boundary known, that the James Webb Space Telescope turned its instruments toward the earliest period of cosmic history and found something that broke the model. The James Webb Space Telescope was designed, among other things, to look further back in time than any previous instrument, to observe the first galaxies that formed in the universe, the structures that assembled from primordial gas in the first few 100 million years after the Big Bang, and to test our theoretical models of how galaxies form and grow against what was actually there. The dominant theoretical framework for how the universe works, the model called lambda CD, which stands for a universe with a cosmological constant and cold, dark matter, made specific, testable predictions about what the early universe should look like. The very first galaxies, it predicted, should be small and faint, because there had not been enough time for the gravitational collapse of gas into stars to produce large, bright, well-organized systems. The first few 100 million years should look like a universe in construction. Rough, early, unfinished. Stars and galaxies building slowly from the bottom up. What Webb found was not that. In its first years of full scientific operation, Webb observed galaxies in the earliest accessible period of cosmic history that were, by the predictions of lambda CDM, impossible, or at minimum, so improbable as to be effectively impossible. They were too bright, too large, too chemically evolved, containing heavy elements that are produced by generations of stellar life and death. Elements that should not have had time to accumulate in such quantities in a universe only a few 100 million years old. The term that started appearing in scientific literature, only half, jokingly, was universe. Breaker galaxies. The record holder, confirmed in peer, reviewed publication in January of 2020, 6, is called MOME Z14, the result of a survey called Mirage or Miracle, designed specifically to determine whether the distant candidate galaxies Webb had been finding were really as far away as they appeared, or whether something else was going on. The answer for MOME Z14 was confirmed. It is a real galaxy, existing 280 million years after the Big Bang, at a moment when the universe was less than 2% of its current age, and it is remarkably luminous, meaning it is producing light at a rate that the standard model cannot explain through any known mechanism, in a time frame that the standard model says should not have produced a galaxy of this maturity. The lead author's public statement on the result was precise in its understatement. We can see farther than humans ever have, and it looks nothing like what we predicted. This is not a single anomalous data point. Webb has found a pattern, a consistent, statistically significant excess of bright, large, mature-looking galaxies at high redshifts, at the earliest observable periods of cosmic history, that are present in numbers roughly 100 times greater than lambda. CDM predicts one anomalous galaxy could be explained. 100 times the expected number cannot be dismissed as a statistical fluctuation. The community response has been varied. Some researchers argue that the star formation efficiency in early galaxies may have been much higher than models assumed, that under certain conditions, Gas collapsed into stars faster than the standard picture allows. Others suggest that early supermassive black holes played a more significant role than anticipated in powering these early galaxies' luminosity. Others argue that the models themselves need more fundamental revision. What is not contested is the observational result. The early universe contains more mature, bright, large galaxies than the dominant theory predicted. And the discrepancy is large enough that it cannot simply be absorbed as a refinement of existing parameters. Lambda. CDM is under pressure. From one direction, the early universe, it is being challenged by what Webb is finding. And from a completely different direction, a different kind of measurement has been converging on the same conclusion. The model that describes the universe we live in may be missing something fundamental. There is a number at the center of modern cosmology that describes one of the most basic properties of the universe: how fast it is expanding. This number is called the Hubble constant, after Edwin Hubble, and it quantifies the relationship between the distance to a galaxy and the speed at which that galaxy is receding from us due to the expansion of space. In principle, it should be a single, measurable value. In practice, it has become the most contentious number in all of physics. Here is the problem. There are two fundamentally different methods for measuring the Hubble constant, and they give different answers. Not slightly different, not within the margin of experimental error, but different in a way that is now statistically significant enough that the probability of the discrepancy occurring by chance is less than 1 in 3.5 million. The first method uses the cosmic microwave background, the oldest light in the universe, combined with the standard cosmological model to calculate what the expansion rate should be today. Given what the universe looked like at 380,000 years old, this method, refined extensively by the Planck satellite, yields a value of approximately 7 kilometers per second per megaparsec, meaning that for every roughly 3 million light years of distance between us and a galaxy, that galaxy is receding at an additional 7 kilometers per second. The second method builds what astronomers call the cosmic distance ladder, a chain of overlapping measurement techniques that starts with the precisely measured distances to nearby stars, steps outward through a class of pulsating stars called Cepheid variables, whose intrinsic brightness is known, and extends to distant galaxies using a type of stellar explosion called a type Ia supernova, which always explodes at approximately the same brightness and therefore serves as a reliable distance marker. This method, developed and refined by multiple independent research teams, yields a value of approximately 3 kilometers per second per megaparsec. 7 versus 3, a 9% difference. And the James Webb Space Telescope, which was partly tasked with resolving this discrepancy by providing more precise measurements of the Cepheid variable stars used in the distance ladder, did not resolve it. Webb confirmed that the Hubble Space Telescope's Cepheid measurements were accurate. The distance ladder result did not move. A new study, published in December of 2025, using an entirely different and independent method, measuring the time delays in light from distant quasars that has been gravitationally bent around intervening galaxies, a technique that requires no Cepheids, no supernovae, no distance ladder at all, found results consistent with the local measurement of 3, adding a third independent line of evidence that the expansion rate in the nearby universe genuinely appears to be faster than the early universe measurement predicts. The discrepancy has reached a statistical significance level called 5 sigma in particle physics, where the 5 sigma threshold is used to define the boundary between not convincing and discovery. Reaching 5 Sigma means that the probability of the result occurring by chance alone is less than 1 in 3.5 million. When physicists at CERN reported the detection of the Higgs boson, 5, sigma was the threshold they needed to cross before announcing a discovery. The Hubble tension has crossed that threshold. What it means, concretely, is this. Either there is a systematic error in both methods that nobody has identified despite decades of effort, multiple independent teams, and now confirmation from the most powerful space telescope ever built, or something in our model of the universe is wrong in a way we do not yet understand. Something is different between the physics of the early universe and the physics of the universe today. Something changed, or something is present that the model does not account for. And here is where the KBC void, the local underdensity we live in, described earlier, enters the picture. If the region of space surrounding the Milky Way is genuinely about 20% less dense than the cosmic average, then the standard expansion rate measurements made from within this void would be systematically biased upward. Matter flowing outward from the underdense region, pulled by gravity toward the denser filaments surrounding it, would add a component to the apparent recession velocities of nearby galaxies, inflating the measured local expansion rate compared to the global background value, living inside the KBC void. In other words, might be making the universe around us appear to expand faster than it actually does at the largest scales. This connection between the structure of the local void and the Hubble tension was explored in a study presented at the Royal Astronomical Society's National Meeting in 2020. 5, which proposed that the KBC void might be large enough and deep enough to account for a significant fraction of the discrepancy without requiring any new fundamental physics. The void alone might be enough, but even if it is, that explanation brings its own problem. The KBC void itself, in the lambda CDM model, should not exist at the scale and depth it is observed to have. The standard model's predictions for how matter should be distributed on scales of hundreds of millions of light years do not allow for voids this large and this pronounced, meaning that if the void is real and as characterized, it is itself evidence of something wrong with the standard model. Just a different kind of evidence. Two different crises, two different symptoms, both pointing at the same underlying condition. A model that has been extraordinarily successful at predicting and describing an enormous range of observations, now being pressured simultaneously from the youngest observable galaxies and from the local structure of the universe we inhabit, not collapsing, but showing cracks of the kind that, in the history of physics, have preceded revolution. We are living at the exact moment when the instruments have become precise enough to see the cracks. The generation before ours could not see them. The generation after ours may have the explanation. We are in between, knowing enough to see the problem, not yet knowing enough to solve it. And if the part of the universe we can see is already this complicated, this full of contradictions and surprises and structures that shouldn't be there, the question that follows naturally is, what is out there that we cannot see? The observable universe, the 93 billion light-year sphere of space from which light has had time to reach us, is not the universe. It is the universe as far as we can currently observe. And the two things are almost certainly not the same. The universe does not end at the particle horizon. Nothing in physics requires it to. Space simply continues beyond the boundary of our visibility, carrying whatever matter and structure and physics exists there, completely inaccessible to any observation we could make today or in principle ever make. Given the acceleration of cosmic expansion, the observable universe is a bubble. Our bubble, inside a much larger and possibly infinite expanse, How much larger? The theoretical framework of cosmic inflation, the period of extraordinarily rapid expansion that occurred in the first tiny fraction of a second after the Big Bang, now supported by multiple independent lines of observational evidence, predicts that the universe expanded so explosively in that initial moment that the region we can observe today is an almost vanishingly small fraction of the total. Depending on the specific inflationary model, the full universe might be at minimum 250 times larger in linear dimension than the observable portion, meaning a volume at least 15 million times greater, and in many models, considerably larger than that. Some models produce a universe that is effectively infinite. Some produce one that is so enormous that the number of observable universe-sized bubbles that could fit inside it exceeds the number of atoms in the observable universe. At some point, the numbers stop being useful as intuition and become purely formal, placeholders for incomprehensibly vast, but inflation produces something else. Something that takes the question of how large is the universe and transforms it into a question that sits uncomfortably on the boundary between physics and philosophy. If inflation happened, and the evidence supports that it did, then the process that caused it was not a one-time event that occurred and stopped. The mathematics of eternal inflation, as the framework is called, indicates that inflation continues to occur in regions of space outside our observable bubble, generating new expanding regions of space, new bubbles, continuously and without end. Each new bubble expands from its own inflationary event, potentially with different values for the physical constants, different strengths of gravity, different masses of fundamental particles, different rates of nuclear reactions, creating a landscape of universes, each with its own physics, each utterly inaccessible to any other. This is the multiverse, not as science fiction, but as the straightforward implication of the best current understanding of the physics that created our own universe. Eternal inflation was not proposed to produce a multiverse. It was proposed because it successfully explained specific observational features of our universe: the flatness of space, the uniformity of the cosmic microwave background, the specific pattern of density fluctuations that seeded all subsequent cosmic structure. The multiverse is the byproduct of that explanation, not the goal. And here is where it gets genuinely uncomfortable. A multiverse produced by eternal inflation is, in principle, impossible to observe or test. By construction, the other bubbles are beyond any conceivable observational horizon. Their physics unknowable, their existence neither confirmable nor deniable by any experiment that could be conducted within our universe. This places it in a strange position, a framework that follows necessarily from a well-supported physical theory, but that itself makes no predictions that can be tested. Some physicists argue that this unfalsifiability disqualifies it as science. Others argue that the framework that generates the multiverse, inflation, is itself so well supported that, accepting its implications, even the untestable ones, is the intellectually consistent position. The debate is ongoing, serious, and unresolved, and it is not a debate between scientists who understand physics and people who don't. It is a debate between physicists of equal technical sophistication about what the word science should be permitted to include. What is unambiguous is this: if the universe is infinite, or even if it is merely the product of an inflationary process that generated a region enormously larger than the observable portion, then the mathematics of probability says something striking. In an infinite universe with a finite number of possible configurations of matter, and quantum mechanics limits the configurations of matter to a finite set within any finite volume, every possible configuration of matter must repeat infinitely many times. Every arrangement of particles that is physically permitted must occur, and must occur infinitely, which means that somewhere, in a region of space that light from our position will never reach, there is an arrangement of matter that is, to within quantum, mechanical limits, identical to the observable universe, identical to our galaxy, our solar system, our planet, the configuration of atoms that constitutes you right now. Reading these words, not similar, identical, not a metaphor, not a philosophical thought experiment, a mathematical consequence of an infinite universe combined with finite configurational possibilities. And yet even this vast, possibly infinite universe filled with repeating configurations, even with all of that, has produced, in the 13.8 billion years of its known history, a silence so complete that, for all the listening we have done, we have heard nothing. In 1950, the physicist Enrico Fermi sat down for lunch with colleagues at Los Alamos, and somewhere during the conversation asked, seemingly as a casual aside, a question that has not been adequately answered in the 75 years since. If the universe is as old as it appears to be, and if even a small fraction of the stars in the galaxy are orbited by planets capable of supporting life, and if life has the tendency to produce intelligence, and intelligence has the tendency to produce technology, then where is everybody? This is the Fermi paradox. And what makes it genuinely difficult, rather than just an interesting puzzle, is the scale of the silence. 2 trillion galaxies, each containing, on average, hundreds of billions of stars. Most of those stars orbited by planets, many of those planets in conditions that could, in principle, support chemistry complex enough to produce biology. And the Milky Way alone is 10 billion years old. Enough time, by the most conservative estimates of biological development, for life to have arisen, evolved intelligence, developed technology, and spread across the entire galaxy many times over. Even a civilization expanding at a small fraction of the speed of light would colonize the galaxy in tens of millions of years, a geological eye blink relative to the age of the Milky Way. And yet, nothing. No signals. No megastructures. No detectable modification of stellar environments that would indicate industrial scale energy use. No artifact in the solar system that arrived from elsewhere. No response to the signals we have sent. The Drake equation, a framework for estimating the number of technological civilizations in the galaxy, yields wildly varying answers depending on assumptions. But even the pessimistic versions leave open the question of why the silence is so complete rather than just sparse. Proposed explanations are numerous. The Great Filter hypothesis suggests there is some step in the development of life or intelligence that is almost universally fatal. Either a step already passed, meaning we are rare survivors, or a step ahead of us, which is the more troubling interpretation. The Dark Forest hypothesis proposes that intelligent civilizations deliberately conceal themselves because the universe is a competitive arena, where detection means destruction. The Rare Earth hypothesis argues that the specific conditions of our solar system and planet are so improbable that complex life is genuinely extraordinarily rare. The Zoo hypothesis proposes that we are being observed but not contacted, for reasons we cannot know. All of these explanations address the biological or civilizational question: why life might be rare, or why it might not communicate. But there is a different framing, one that the preceding chapters of this documentary have been quietly building toward, which approaches the silence not as a puzzle about biology, but as a consequence of architecture. Consider what we now know about the structure of the universe. The typical separation between galaxies is millions of light years. The typical void is hundreds of millions of light years across, and the Milky Way sits inside one. The expansion of space means that beyond a certain distance, no signal can ever arrive. The universe is not just large, it is actively pulling things apart. Even within the Milky Way, within a single galaxy, the distances are so large that a signal traveling at the speed of light would take 100,000 years to cross from one side to the other. And any civilization sending a signal has no way of knowing whether the recipient still exists, whether the planet is still habitable, whether the species has survived the 100,000 years of waiting for a reply. Recall Voyager and the Golden Record. Humanity has physically sent an object into space carrying a message, the most ambitious attempt at contact our civilization has made. That object will not pass within 2 light years of any star for 40,000 years. If another civilization had made an equivalent gesture at any point in the past 40,000 years, aimed in our direction, it would not have reached us yet. If they had made it 100,000 years ago, it might have, but we had no instruments to detect it until roughly the past century. The window of overlap between the transmission of a signal and the existence of a receiver capable of detecting it is extraordinarily narrow when compared to the timescales over which signals travel. The universe may not be silent because we are alone. The universe may be structured in a way that makes silence the expected outcome, even if the cosmos is full of life. A kind of quarantine not imposed by any agency, but built into the physics. The distances are too large, the expansion too relentless, the event horizons too absolute, the timing required for 2 civilizations to be within communication range simultaneously too precise. For the contact we imagine to be anything but extraordinarily improbable, and yet here we are, asking the question, which in its own way is perhaps the most remarkable thing about our position in all of this. On February 14th, 1990, as the Voyager 1 spacecraft was preparing to leave the inner solar system, the astronomer Carl Sagan persuaded NASA to turn its camera backward, back toward the direction from which it had come, and take a photograph of Earth from a distance of approximately 6 billion kilometers. In that photograph, Earth appears as a pale blue dot, a fraction of a pixel, suspended in a ray of scattered sunlight. With the darkness of space on all sides, everything that has ever happened to a human being happened on that dot. Every war and peace treaty, every scientific discovery, every act of love and cruelty, every king and slave, every idea that changed history, every person who ever looked up at the sky and wondered what was out there, they were all on that dot, and from 6 billion kilometers away, which is a vanishingly small distance compared to even the nearest star. The dot is barely visible. Now take everything described in this documentary. The Milky Way, with its 400 billion stars, itself just one of 2 trillion galaxies in the observable universe. The observable universe itself, a bubble of finite visibility inside a possibly infinite space. The whole thing built from matter that is only 5% of what exists, scaffolded by dark matter we cannot detect, accelerated by dark energy we cannot explain. Its own model of structure, broken simultaneously by the oldest galaxies we have ever seen and by a discrepancy in the most basic measurement of cosmic expansion. And place the pale blue dot inside that context. You are made of atoms forged in the cores of stars that lived and died before the sun existed. The iron in your blood was produced in a stellar explosion, scattered across space, incorporated into the gas cloud that became the solar system, concentrated by geological processes into the biosphere, metabolized into your body, the calcium in your bones, the oxygen you use to process these words, the carbon in every molecule of your body, all of it assembled by stellar nucleosynthesis over billions of years, scattered by stellar death, gathered by gravity into a new generation of star and planet, and eventually into you. This is not a poetic metaphor. This is the literal physical history of the atoms that constitute your body, traceable through astrophysics to specific types of stellar events, at specific points in cosmic history, in specific parts of the galaxy. You are, in the most concrete physical sense, a piece of the universe that has been rearranged by 4 billion years of biological evolution into a configuration capable of studying the universe from the inside. 13.8 billion years of cosmic history. The Big Bang, the formation of the first stars, their lives and deaths, the assembly of the Milky Way, the formation of the solar system, the cooling of the Earth, the origin of life, the entirety of biological evolution, all of it, in some sense, was required to produce the conditions in which you exist and can ask the question of where you are and what all of this is. And here is what is genuinely striking about the moment in history we occupy. The model that describes all of this is breaking, not collapsing, not being discarded, but developing the kind of cracks that, in the past, have indicated that our understanding of the universe is approaching a boundary where the existing framework is insufficient and something new is required. The early galaxies that should not exist, the expansion rate that measures differently from two directions, the void that should not be as deep or as large as it is. Each of these anomalies is, in isolation, a puzzle. Together, they suggest that the universe is telling us something we have not yet learned to hear correctly. Every major revision in our understanding of the cosmos, Newton's gravity, Maxwell's electromagnetism, Einstein's relativity, the development of quantum mechanics, was preceded by exactly this kind of period. Anomalies accumulating, models straining, measurements refusing to reconcile. The resolution, in each case, was not the abandonment of everything that came before, but its absorption into a larger framework, a new lens through which the old observations still made sense. And the anomalies were resolved, and new questions opened that the previous framework had not been able to ask. We do not know what that framework will look like. We do not know whether the resolution of the Hubble tension will require a modification of dark energy, a revision of inflation, a rethinking of how structure grows, or something else entirely. We do not know whether lambda CDM will be replaced or extended. We do not know whether the early galaxies Webb is finding will force a complete rethinking of star formation physics, or whether some refinement of existing models will absorb them. What we do know is that the instruments exist, right now, to see the problem clearly for the first time. The James Webb Space Telescope is still operating. The Dark Energy Spectroscopic Instrument is mapping the universe's structure with unprecedented precision. The Euclid satellite is building an independent map of cosmic structure. The data is coming in, and it is not confirming what we thought. It is complicating it, deepening it, pushing the questions into territory we did not know needed to be explored. The question that opened this documentary, whether the universe looks like what we predicted, has been answered. It does not. And that answer is not a reason for alarm, but for attention, because every time the universe has refused to fit our expectations, the result has been a deeper and stranger and more beautiful understanding of what we are actually living inside. The pale blue dot is still there, 6 billion kilometers from where Voyager 1 was when it took the photograph. Voyager 1 is still moving, carrying its golden record, its encoded message, its portrait of a species that wanted to reach out, through interstellar space, toward an Oort cloud boundary it will not reach for 300 years, and a nearest star it will not pass for tens of thousands of years. sending a signal back home that now takes more than 3 hours to arrive. And on the dot, the atoms of former stars are still asking questions. That is, perhaps, the most accurate description of what we are, the part of the universe that became curious about the rest of it. Not the center of it. We are not that, not the most important part. Nothing in physics suggests any part is more important than any other. But the part that turned around, looked at the whole, and decided to try to understand it. In a universe that is mostly dark matter and dark energy, in a universe where 5% is all we can study, in a universe where the model is cracking and the distances are incomprehensible and the silence is absolute, the fact that understanding is happening at all is the thing worth sitting with at the end of this. Not because it resolves the mystery, but because the mystery is still open, the instruments are still running, and somewhere in the data coming back from the edge of the observable universe, the next piece of the answer is already waiting to be found.